Welcome to the Crazy Hat Chemist. So here we go with another video on acids, bases, and titrations. Bam! So this is the second example here, and it is part C of this second example. We're doing the equivalence point calculation. This equivalence point calculation is the most complicated of all the calculation parts on an acid-base titration problem. Okay, so equivalence point calculation, here we go. Make sure that you review actually part A, part B before you start this part C. Okay, because part A has all the initial steps of the problem and all the beginning parts of this problem. So we're going to calculate the moles of base, that is the moles of the ethanolamine. Okay, and that is, we have 25 mils of ethanolamine and it has a molarity of 0.010 moles per liter. So 25 mils. Then the next unit conversion is converting the milliliters into liters. That's 1 liter is 1,000 milliliters. That way our volume of milliliters will cancel out, such that the third and final unit conversion is the molarity, which is 0.010 moles per 1 liter. Now our liters cancel out. Now we have moles of ethanolamine, which is 0.00025 moles of ethanolamine, and that formula is HO, CH2, CH2, NH2. Okay, so at the equivalence point, the most important part here that drives the math is that at the equivalence point, the moles of the base is equivalent or equal to the moles of the acid. So how many moles of hydrochloric acid do I have? The same as the moles of the ethanolamine, which would be 0.00025 moles. Okay, so that is the moles of the acid that is required or necessary at the equivalence point. Okay, now I need to calculate the volume that's required. So we're going to calculate the volume of the acid that is necessary at the equivalence point. I have the moles of the acid and I have the molarity of the acid. So I have the moles of the acid, that's 0.00025 moles. Now I'm using the molarity of the acid, which is 0.0095 moles per 1 liter. Remember, I had to take the reciprocal of that such that I keep the moles with the numbers and the moles with the 0.0095 and the 1 with the liter. That way the moles cancel out. Then I'm going to convert this liters into milliliters with my unit conversion of 1 liter is equal to 1,000 milliliters. Okay, and that will give me 26.3 milliliters of HCl that's required at the equivalence point. Okay, now I'm going to calculate the total volume at the equivalence point. So I had the amount in volume in milliliters of the ethanolamine, which is 25 mils, plus the 26.3 milliliters of hydrochloric acid that's necessary at the equivalence point. So that's 25 mils of the base ethanolamine plus the 26.3 milliliters of the acid, that's the hydrochloric acid. That will give me a total volume of 51.3 milliliters. Okay? All right, now we're going to calculate the concentration of the conjugate to the base. The base reacts with the acid, and that base has been completely converted into its conjugate acid, and it's going to be now in a new volume with the addition of that hydrochloric acid at the equivalence point. So the concentration of the conjugate acid of the base is the same as the moles that we had divided by our new volume. So the moles of the ethanolamine is equivalent to the moles of its conjugate acid. Okay, that's 0.00025 moles of the conjugate acid to ethanolamine divided by the total volume in liters, because I want to get molarity. So that total volume in liters is 0.0513 liters. Now I'm going to get this value. This is 4.9 times 10 to the negative 3 molar. Okay, I'm going to use this value for a new ice table. So at the equivalence point, all of the base has been converted to its conjugate acid. Therefore, a new equation must be written with an appropriate new K value. Okay, we're going to start with the conjugate to the base for the next ice table. That is that conjugate acid that is right there. Okay, all right, so quick little intermission here, and you can donate to my website. Super cool. Get a sticker. I'll send one to you. Or you could donate to my website and, get a t-shirt. Check it out. And on the back, There's the front, there's the back. Gotta get one of those. All right, there's the merchandise here for the Crazy Hat Chemist. Bam! Okay, so this is the conjugate acid to ethanolamine plus the water. I'm going to write the conjugate pairs on the other side, which is, of course, going to be ethanolamine itself and the hydronium ion. You should see that both sides of this equation have the same charge. That is a +1 charge. That's a net charge of +1 on the reactant and the product side. Okay, the conjugate pairs are plus or minus a hydrogen of each other. We're going to do an ice table of this. So that is the initial, the change, and the equilibrium. We just derived the conjugate acid concentration from the previous slide, and that value is going to go right there. That's 0.0049. Okay, there's going to be nothing for the water because that's a liquid, and liquids are not involved in any K expression. Now, this is like any other equilibrium or ice table, and that is I start off with something on the reactant side, and what do you have on the product side? Initially, nothing. Nothing on both products on the product side. Okay, now the change is going to be the same as any other equilibrium problem as well, and that is on the reactant side you're going to decrease the reactants, on the product side you're going to increase the products. So on the reactant side it's going to be a -1x. I'm using the stoichiometric coefficient on the conjugate acid to ethanolamine, that's a 1. Okay, I don't have to worry about the water because that's a liquid. And on the product side, I have ethanolamine, that has a stoichiometric coefficient of 1, and that's going to be a increase, which is a +1x. The hydronium ion has a stoichiometric coefficient of a 1, and that's going to be a +1x as well. I'm going to add up my I and my C for my ice table and to get my equilibrium values here. So that's going to be 0.0049 minus x. Nothing for the water, and just x for the ethanolamine and x for the hydronium ion. Now, I need to ask myself, what kind of K am I using? And it is all dependent on what's on the product side. Do I see a hydroxide or a hydronium ion on the product side? So I see a hydronium ion on the product side. Therefore, I'm going to have to write a Ka. This is a Ka. If it had a hydroxide, it would be a Kb. But this has a hydronium, so it's going to be a Ka. So I'm going to write the Ka expression for this. That's products over reactants with the stoichiometric coefficients as exponents like any other equilibrium K. So that is the ethanolamine times hydronium ion divided by the conjugate acid to ethanolamine in the denominator there. Okay? I'm going to be using the Ka. So I need to derive the Ka. Now, I'll given as a known value the Kw, and on the initial problem in part A, you were given a Kb for ethanolamine. So I'm going to plug in the Kb at 3.2 times 10 to the negative 5 and the Kw at 1.0 times 10 to the negative 14 and solve for the Ka. That's going to be 3.1 times 10 to the negative 10. That's going to go right here. Now I'm going to plug in my equilibrium values from my ice table into that Ka expression, and this is what I'm going to get. So now I have 3.1 times 10 to the negative 10, that's the Ka that was derived, is equal to x times x, which is x squared in the numerator, divided by the 0.0049, okay, minus x. Now, again, we always need to ask ourselves, are we going to be using the quadratic equation? Thus far, we haven't, but this time, do we or do we not? And we are going to be using this concept here. That is, if 100 times the K, if that is less than the initial concentration, then I'm going to use the approximation and I will not be using the quadratic. So, 3.1 times 10 to the negative 10, that is the Ka in this case. 100 times that. Is that less than 0.0049? Yes, it is. And since it is, we are going to get rid of this minus x in the denominator, and therefore we do not have to be using the quadratic equation. Okay, now I need to solve for x. Solving for x is going to be very simple. That's 3.1 times 10 to the negative 10 times 0.0049. Take the square root of that. That will be equal to x. X is equal to 1.2 times 10 to the negative 6. Now, I'm going to look at my ice table. Figure out what does x equal. X equals the ethanolamine concentration and the hydronium ion concentration. So if you were asking for the ethanolamine concentration at the equilibrium concentrations, that would be 1.2 times 10 negative 6 molar. If it's the hydronium ion concentration that you're looking for, it's 1.2 times 10 negative 6 molar. And that's what I have right there. The hydronium ion concentration is 1.2 times 10 to the negative 6 molar. Okay, now I'm trying to solve for the pH here. So how do I get the pH from the hydronium ion concentration? I'm going to take the negative log of this value. The pH is equal to the negative log of the hydronium ion concentration. And that pH is going to equal 5.92. Okay, now I'm going to ask myself, does this number of 5.92 seem to be a reasonable value for the pH at the equivalence point or the end point of this titration? So it's a weak base with titrating it against a strong acid. Okay, at the equivalence point, the acid overwhelms it. Okay, so therefore this pH should be less than 7, of which it is, and that absolutely makes sense. So yes, it's acidic, as you would predict and would expect. It's certainly not a pH of 7. A pH of 7 at the equivalence point applies to a problem where you have a strong acid and a strong base titration, or a strong acid and a strong base, strong acid titration. Okay? Okay. So what is the best indicator to use for this titration at the equivalence point? And what matters is the equivalence point pH. So since the pH at the equivalence point is equal to 5.92, that's the equivalence point or the end point, one would choose or should choose an indicator of which changes color at or around this pH. So, or if one knows the pKa of the indicators, then one would choose an indicator where the pKa matches or closely approximates the pH at the equivalence point as much as possible. So upon analysis of a previous chart and table that I had in my previous videos, brome cresol purple would be the best indicator, as it changes from a yellow when it's acidic to a purple above a pH of 6. So that would be right in that range of 5.92. Perfect indicator to use for this particular titration. Okay, I am the Crazy Hat Chemist, and of course, you know, I've got myself a crazy hat, and give me a thumbs up if you like that video, subscribe to my YouTube channel, and get yourself a sticker. Okay, talk to you later. See you next time. Bye now.